Having looked at the general definitions and relationships between the vectors position, velocity, and acceleration, we now look at a special type of situation where problems are very easy to solve. This situation is when acceleration is constant. If during a journey there is a period of time where an object's acceleration doesn't change, we can derive some very simple equations which we can quickly use to figure out missing information about the object's motion. Let's say that this object has a constant acceleration a, and that our time period that we are interested in starts now, at time t equals 0, with its position at some imaginary origin. For any future time, we want to be able to relate the object's displacement from the start point, s, its initial velocity that it had at the start point, u, the final velocity that it has at the future time, v, its constant acceleration, a, and the amount of time that has passed, t. Now to derive these relationships, known as the SUVAT equations. The object's velocity as a function of time is found by integrating the acceleration with respect to t. Acceleration is just a constant, and so integrating it brings a t term to multiply the a, and a plus c. To find what c is, we evaluate the new function at a point that we know. We know that when time t is equal to 0, the object's velocity is u, its initial velocity, and so the c must be u. Therefore, the velocity v at time t is v is equal to u plus at. The object's position is found by integrating the velocity function. Again, by following the standard integration rules, we obtain that the position is ut plus 1/2 at squared plus c. Again, we find what the c is by evaluating the position at a point that we know. We know that at time t is equal to 0, the position is 0, and so c must be 0. Therefore, position s is equal to ut plus 1/2 at squared. These two equations alone actually hold all the relevant information we need, but it is useful to rewrite them in a couple more ways to make solving problems quicker. The first way we do this is to express this top equation in terms of t, and then substitute it into the other equation. We do the algebra to expand the brackets and tidy it up, and obtain that v squared is equal to u squared plus 2as. The second way that we do this is to write the top equation in terms of a and sub it into the other equation. A bit of algebra shows us that s is equal to v plus u over 2 multiplied by t. Each of these equations contain 4 of the variables of interest, and when solving problems, you will always find yourself knowing 3 of these variables and needing to find the last. The only task is then to pick the equation which contains the 3 variables that you know and the one that you want, and to rearrange it as required.